Can I start, sir? Okay. Good morning. So this is Harika Palamani, Physics faculty from PW. Today we are going to discuss about KTG, Kinetic Theory of Gases and Thermodynamics for today's session. So let us start the today's session. First, we are going to discuss about kinetic theory of gases before entering into the thermodynamics. So these are the topics from kinetic theory of gases that we are going to discuss today. First, we'll discuss what is kinetic theory of gases, what are the assumptions for the kinetic theory of gases or postulates, okay, and basic introduction of the kinetic theory of gases. And then we will continue with energy of gases, what is an ideal gas, what are gas laws, and the concept of mixture. So these are the important topics in the kinetic theory of gases that we are going to discuss today and revise all of them in a detailed way. Okay. So let us start today's session. Once again, welcome to all of you and good morning. Fine. So this is the previous year exam analysis. Okay, so here the number of questions in this column, it is number of questions and years. So if you can see from 2015, okay, to 2024 it is. Okay, so in 2015, one question, two questions in 2015, and in 2016, when it is conducted in second time, it is two questions. In 2016, when it is conducted first time, there are no questions, came from the KTG, and from 2017, it is again two questions. So one in 2020, if you see, okay, there are three questions, okay, from the KTG, Kinetic Theory of Gases, from 2021, 22, 23, 24. Consistently, we are getting at least minimum one question from the KTG. Though, so this is the previous year paper and previous year exam analysis. Okay, so let us start the introduction with the kinetic theory of gases. Okay, so kinetic theory of gases. In this, we will learn about basically the ideal gas. Okay, and we will see what is a real gas. Okay, real gas means it is a gas we generally see in the nature. Okay, so it's a normal gas which we generally observe and see and feel in the nature. Okay, but the ideal gas, it is a theoretical gas. Okay, so theoretical gas. Okay, real gas is the natural gas which we usually see in the nature. Okay, so in theoretical gas, negligible volume is there. Okay, or else we can also consider it. We also can consider that in ideal gas there will be no volume also. Okay, so negligible volume. Okay, in real gas, volume will be there. Okay, so volume is there. Here it is not at all negligible. Okay, next. Here what happens in ideal gas, so it is a theoretical gas by random motion. Okay, it is a theoretical gas by random motion. Okay, of point particles. Okay, and this motion is through elastic collision. Motion is through elastic collision. Okay, here because of elastic collision in ideal gas there will be no loss of kinetic energy. Okay, no loss in kinetic energy. When it comes to the real gas, gas particles will collide normally. So because of the collision, there will be a loss in kinetic energy. So there is a loss in kinetic energy. So there is a loss in kinetic energy due to collision. Due to collision. Okay. So in ideal gas, there will be no loss in kinetic energy, and in real gas, there will be loss in kinetic energy due to the collision. Whereas, so usually in a summary, if I want to tell what is an ideal gas, it is a basically a theoretical gas, okay? So theoretical gas by random motion of the particles, okay, through elastic collision. So we know that elastic collision means there will be no loss in the kinetic energy, correct? So yeah, real gas behaves as ideal gas. So real gas behaves as ideal gas at high temperatures. So this is the condition when real gas acts as an ideal gas. Okay. So it is a high temperatures and low pressures. So at high temperatures and low pressures, a real gas acts as the or behaves as the ideal gas. This is the important. Okay. So one more theoretical bit where there is a chance in getting from the real gas and ideal gas. Ideal gas means, okay, the energy exerted by the gas molecules or gas particles, okay, energy exerted will be only due to the kinetic energy, because as I told you, ideal gas, okay, so ideal gas means it is a theoretical gas which is like by the motion of the random motion of the particles, correct? So it will be only due to, so motion means velocity, so the energy possessed by the virtue of its motion is the kinetic energy, correct? So ideal gas means only kinetic energy will be there, whereas for real gas, okay, kinetic energy plus potential energy will be there. This is the difference between ideal gas and real gas. Okay, in 1 year we got the bit on this theory part. Okay, so ideal gas means only kinetic energy, real gas means kinetic energy plus the potential energy. Okay, so this is the difference between ideal gas and real gas. In kinetic theory of gases, we will study, it is the study of ideal gas. It is a study of ideal gas. So in this kinetic theory of gases, we will study about the gases. Okay, which type of gas we'll study? We'll study the ideal gas. Okay, so motion of the particles and all we will study in this chapter. So this is the difference between ideal gas and the real gas. When real gas acts as ideal gas at high temperatures and low pressure. Ideal gas means only the kinetic energy, and real gas means kinetic energy plus potential energy. Okay. Now assumptions that we made in the kinetic theory of gases, or we can also say this as a postulates of kinetic theory of gases. So first we'll see what is the first assumption or first postulate. The molecules of a given gas are identical. Okay, so the molecules, what is the first point? The molecules of a given gas all are identical but are different than those of the other gas. Okay, each and different gases are having different identical particles in it. Okay, now the gases, the molecules of gases are, okay, the molecules of gas are identical, spherical, rigid, and perfectly elastic point masses. So molecules of gas is identical. Okay, all, for example, you take one gas, hydrogen. Okay, all the molecules in the hydrogen atom will be, sorry, hydrogen gas will be identical, and they are spherical, rigid, and perfectly elastic. And molecules of a gas keep on moving in a random, so I told you, right, ideal gas is a motion of random motion. Okay, so moving randomly in all possible directions with all possible velocities. Okay, speed of gas lies between 0 to infinity. Speed of gas lies between 0 to infinity. If you can see here, consider this as any gas. Okay, so all these particles are the gas particles, all the circles, so they can move and collide with the particles, and the collision happens because of this collision. So particle gets collision with each other, correct? So because of this collision, there will be no loss in the kinetic energy, because collisions are elastic. So you can write here elastic collisions. Clear, ma? Next, there will be no attractive or repulsive forces between gas molecules. And density of gas, obviously density of gas is constant at all points of the container. So if you see here, this is the container in which we are having the gas particles. All gas particles are moving randomly in all possible directions with all possible velocities, correct? So after collision, colliding with the walls of the container, they will again come back because the elastic collision, right? Collisions here in the container are elastic collision, so no loss of kinetic energy. Okay, so due to their momentum changes, only momentum changes. Okay, that is also transferred, that's it. Okay, Nana? Next. Now, till now we have discussed about the ideal gas only. Okay, so again I will repeat the ideal gas. Okay, theoretical gas. Okay, it is a theoretical gas by random motion of point particles through elastic collision, which is called the ideal gas. Okay, so if you take a container, there are so many particles, gas particles, all are identical. Now one more thing is also there, Nana. All are identical particles. They are small compared to the distance between them. One more point, okay. The particles, gas particles of an ideal gas, okay, are small. They are very small compared compared to distance between them. Okay, compared to distance between them. Equation of state for the ideal gas. So the ideal gas equation is PV is equal to nRT, or this can also be written as PV is equal to mu RT. Okay, here P stands for pressure of gas or pressure on gas. Okay, either it can be pressure of the gas or it can be pressure on the gas. Next, V is volume of the gas. V is volume of the gas, where mu or N are number of moles present in the gas. Next, where R is universal, where R is universal gas constant. Okay, so the value of R is 8.314 mole per gram calorie. Okay, next, where T is the temperature, and it will be in terms of Kelvin or degree Celsius, depending upon the answer that we get it in the options. Okay, so pressure will be, unit of pressure will be Newton per meter square, force by area. Volume will be meter cube or centimeter cube. Number of moles, it is a scalar quantity, correct? So PV is equal to mu RT. Okay, now see here, Nana, what is in here? Number of moles. Okay, number of moles, what is the formula? Given mass by molar mass, correct? Given mass by molar mass is the number of moles formula, or molecular weight also you can consider. From here, if I write PV is equal to given mass, if I consider it as small m, and molar mass if I consider it as a capital M, mu in the place of n or mu, I can write it as m by capital M, correct, into RT, right, Nana? So PV is equal to nRT. From here, PV is equal to, what is N? N is the given mass by the molar mass. So given mass by the molar mass into RT. From here, if I send this volume to this side, it becomes M into V by RT. Here, volume is in numerator, correct, in LHS side. If it comes to this side, it will be in the denominator. Now, mass by volume, mass is the given mass of the gas, correct, and volume. So, given mass by given volume gives us the density, right? What is the density formula? Density formula is mass by volume, correct? Mass by volume. So, pressure is equal to density by molecular weight or molar mass into RT. This is the formula of pressure in terms of the density. Okay, so we are having PV is equal to nRT, correct? From here, P is equal to N by V RT. This I can write it as, see, I am writing the possible ways of the formulas. Okay, so in question they can ask anything, right? So I am writing all the formulas which are suitable to solve the questions. Okay, so P is equal to, one more formula is density RT by N. So these are the formulas. Okay, and here we can also write PV is equal to molar mass by molecular weight into given mass of the volume into universal gas constant into the temperature. Correct, Nana? So what are the formulas I kept in the boxes? Those all are very important. Okay. Next, properties of ideal gas. As we discussed, there will be elastic collision, as we discussed already, no loss, no loss in kinetic energy. Okay, NTP and STP. NTP means normal temperature pressure. Normal temperature pressure. NTP means normal temperature pressure. So at NTP, temperature is 20 degrees Celsius. Okay, or if I convert into Kelvin, temperature will be 20 plus 273 degrees to Kelvin, right? So sorry, degree Celsius to Kelvin. Okay, 20 to 273 is 293 Kelvin, and the pressure will be 1 atmosphere. So 1 atmosphere is the normal pressure. 1 atmosphere means in pascals. If you convert it into the pascal, it becomes 1.013 into 10 to the power 5 pascal. This is the normal pressure. Next, STP, standard pressure. STP, standard temperature and pressure. STP means standard temperature and pressure. What is a standard temperature? Standard temperature is at 0 degrees Celsius, or if I want to convert it into Kelvin, 0 plus 273, it becomes 273 Kelvin. Okay, so these are the NTP and STP. Next, find the number. So we'll solve few questions. Find the number of molecules in 30 centimeter cube of an ideal gas at 27 degrees Celsius at a pressure of 1 atmosphere. Okay, you have to calculate the number of molecules. So we know the from ideal gas equation PV is equal to nRT, correct? From here what you have to calculate? You have to calculate n value, but here instead of universal gas constant, they have mentioned to take Boltzmann constant. Okay, they have mentioned to take Boltzmann constant. So here we will take, instead of R, we will take it as Boltzmann constant n. Here it will be pressure into volume. So pressure into volume is equal to number of molecules into kBT. Okay, from here n value I can write it as PVE divided by kb into T. So by using this formula we can solve the this question. So usually what the questions I used to hear from the students is like, we are able to see the question, we are able to understand the concept when it comes to the application of numericals, or then it comes to the, solving the numericals, they feel so much of difficulty, in identifying what formula to be used and how to solve that numerical. They'll get confused. So I only tell one thing to those students who are facing this problem. Okay. So whenever you see a question, you don't just go to the solve the question. Okay. You just first write the given data. Okay. Writing given data will half solve your problem. Okay. By writing given data, that you might know, right? This question is coming from particular chapter. So because whatever given data provided in the question, based on that data you can get the formula, and then you can substitute the values. See here, PV is equal to NRP. Okay, first we will write the given data. Volume, it is given as 30 centimeter cube. Convert it into meter cube. So it becomes 30 into 10 to the power minus 3. Correct. 10 to the power minus 3. 1 meter is equal to 10 to the power minus 2. So it is 2. 10 to the power minus 2 meter cube. Okay. So this will become how much? If I convert, after converting, it becomes volume is equal to 30 into 10 to the power minus 6. Hmm. 10 to the power minus 6 meter cube. Okay. Next, what is the temperature? Temperature given as 27 degrees Celsius. Converted into Kelvin, it becomes 27 plus 273. This becomes 300 Kelvin. Pressure, it is given as 1.38 atmosphere. 1 atmosphere is equal to 1.38 into how many pascals? 1.013 into 10 to the power 5 pascals. Okay. So now we can ready, or we are ready to substitute in the formula. Number of molecules is equal to, what is the pressure? 1.38 into 1.013 into 10 to the power 5. Okay, pressure into, what is the volume? Volume is 30 into, okay, what is the pressure? No, no, sorry, volume 30 into 10 to the power minus 6. This is the volume, divided by, what is the Boltzmann constant value? 1.38 into 10 to the power minus 23. What is the temperature? Into 300 Kelvin. So see now, here 1.38 into 1.013. This you can consider it as 1.4. Okay, 1.38 into 1.013. So 1 to 3. So if we do the multiplication, we'll approximately get 1.41. Okay, and divided by 1.38, and here also into this you will get it as 30 into 10 to the power minus 6. This you will get it as into 300. So by doing 1.41 into 30, this approximately we can take it as 4.1. This is also, you can consider it as 4.1. Here 10 to the power minus 23 is there. 1 into 23, here value will be there. It goes 1 into 10 to the power 21 is the answer. So first step. Okay, Nana? So in this way you can solve. Next, calculate the temperature of sun density is 1.4 gram per centimeter cube. Pressure is 1.4 into 10 to the power 9 atmosphere. Average molecular weight of gas in the sun is 2 grams per mole. Okay, you have to find the temperature, calculate the temperature. So what is the formula I have given? P is equal to density into RT by molecular weight. This formula we have derived since in the starting of the class. From here, temperature means pressure into molecular weight by RT. This is the formula, correct? So T is equal to, what is the pressure given? 1.4 in atmosphere it is given, right? So 1.4 into 10 to the power 9. 1 atmosphere is equal to 1.013. 1.013 into 10 to the power 5 Pascal, correct? Divided by Molecular weight. What is the molecular weight? It is given by 2 kgs. You convert it into kgs, it becomes 10 to the power minus 3 per mole. This is the molecular weight. Next, what is RT? RT will be 8.4 joule. You can take it as 8.4 into what is the temperature that we have to find out. Correct. Next, what else is there? Density, right? Density. What is the density given? 1.4. This also you have to convert it into 10 to the power minus 3 meter cube, right? It will go into 10 to the power 6. This is the density. So temperature will be how much ma? Calculate 1.4 into 1.013. Okay, so this value you will get it as into 2 1.4 into 1.013. So 1.4 into 1.013, 12, 4 ones are 4, 5, 0, 1, 3, 1, 0, 1. So 2, 8, 1, 0, 1, 1, and approximately you will get it as 4 zeros after. So 1.1. Okay, so this you will get it as 1.5, like that you will get. Okay, 1.5, 1.1 into 10 to the power 4 into 2. This approximately you will get it as 3. 8.4 into 1.4. So 8.4 into 1.4, 16. 8 fours are how much? 8, 10, next. 32. 8 plus 3 is how much? 11. So 1, 2. So 11.76. Okay. So 11.76, this I can write it as 3, 1.5 into 1.5, it is 3 by 11.6, 3 ones are 3 threes. So 3.8 you will get. So 1 by 3.8 value is 0.8, 0.08. So together you will get 0.8 into 10 to the power 7 Kelvin. So this is the answer. Okay, Nana? So this is the process. Next. So these are the numericals, basic numericals that these are the models that we get in the exam based on ideal gas. Next, gas laws. Okay. So gas laws. First law is Boyle's law, Charles' law, Lusak's law, Avogadro's law, and Dalton's partial pressure. Okay. So first we'll see what is Boyle's law. Boyle's law. Okay. So Boyle's law means the pressure is inversely proportional to the volume. Okay, pressure of a given gas is inversely proportional to volume. This is the Boyle's law. Okay, now you see none of these are the important graphs. Okay, so PV is equal to mu RT, where P, if I send V that side, it becomes inversely proportional to volume, right? At a constant temperature. What I told? At a constant temperature. Correct, at a constant temperature, pressure is inversely proportional to volume. So from here I can write PV is equal to constant. Now if we go to the graphs, okay, PV inversely proportional means graph will come in the curve part. Here if you see temperature is a constant here also, and here you can take temperature is constant, here it is the inverse of volume. Next, at NTP of a gas is changed to one third of volume. at constant temperature, then the new pressure will be at NTP. At NTP means what is the pressure? It is 1 atmosphere. Okay. So P1 V1 is equal to P2 V2 is the initial pressure at atmosphere. So options also it is given in 1 atmosphere only. So we here we will take it as 1 atmosphere. Volume is how much? V1. Okay, we will take it as V1. We have to consider the new pressure only when the volume gets changed by one third of its initial volume. Correct. Now what we can cancel? V1 gets cancelled. P2 by 3 is equal to 1 atmosphere. From here I can take P2 is equal to 1 into 3 atmosphere. So P2 is equal to, what is the answer? 3 atmosphere. So answer is the third option. Okay. Next, Charles law. Charles law is, okay, at a constant pressure, volume is inversely proportional, directly proportional to the temperature. Okay, Charles law. At constant pressure, volume is directly proportional to temperature. So in comparison of two gases, in comparison of two gases, V1 by V2 is equal to T1 by T2. This is the comparison of the Charles law. Next, directly proportional. So these are the graphs between P and V. Okay, so pressure is a constant here. Here also pressure is the constant. V by T means it is a pressure only, right? So it is a constant. Between V and T, pressure is constant. Okay, from here also it is constant. Okay. Next, Lusak's law. According to it, at a constant volume, pressure is directly proportional to the temperature. From here you can write comparison of two gases means P1 by P2 is equal to T1 by T2. These are the graphs. So here volume is constant, temperature and pressure and temperature is inversely proportional. Here volume is constant. So these are the graphs for the Charles law. Next, match the correct. Volume is increasing, volume is constant, temperature is constant and pressure is constant. First P, we will match it with volume is increasing. Here volume is increasing. So which graph? Volume is increasing. So in this Q means volume is constant. If you see here, there is no change in the volume. So Q belongs to D. Next, temperature. Pressure is constant. In which pressure is constant? P. Sorry. Pressure is constant in C graph. Next, in R. R. Temperature is constant. PV. Correct. So it is constant means R belongs to B and P belongs to volume is increasing. See here, volume it is increasing. So it is A. Next, the cylinder contains a gas of 2 into 10 to the power 5 Pascal and at 47 degrees Celsius. Cylinder is steadily heating, neglecting any change in its volume. Neglecting any change in its volume means volume remains constant. Neglecting any change means volume remains constant. Okay, so volume here remains the constant. So at constant volume, pressure is directly proportional to temperature. Comparison means P1 by P2 is equal to T1 by T2. Okay, so what is given? P1 value 2 into 10 to the power 5 by what is P2? Maximum pressure will be 8 into 10 to the power 5. P1 by P2 is equal to T1. What is the temperature? 47 degrees is given. Convert it into Kelvin, and T2 you have to find out. T2 is equal to 1040. Okay. So T2 is equal to by 4. If you send 2 to that side, 47 plus 273, 0, 12, and this is how much? 3. Okay. Hmm. So 320. T2 is equal to 320 into 4. So 4 zeros are 0, 4 twos are 8, 4 threes are 12. So what is the answer? T2 is equal to 1280 Kelvin. This is the answer, Nana. Why we have converted 20, 47 degrees to Kelvin is because temperature T2 they are asking in the Kelvin. So answer is first option. Understood, everyone? Correct. So here in this question, nothing is given actually. Okay, so neglecting any change. So you have to negligible volume, right? Negligible volume means there is no volume. No change in volume means here volume will be the constant. Okay, so you can take at the constant volume, pressure is changing with respect to the temperature. Okay, so we have to, if you want to take the relation, how this relation came is PV is equal to nRT, correct? Now here volume is constant. For example, P is equal to, I can take nR by V into T, right? So N, anyways, number of moles is a constant. R is a universal gas constant, which is 8.314. And volume also we are considering as a constant because in the question, it is clearly mentioned that we have to neglect the volume, correct? So if I neglect this, both are, if I take all these terms as a directly, I mean, proportional. So pressure is directly proportional to the temperature. That's it. Okay. Avogadro's law. So see here, according to it, at same temperature and same pressure, equal volume of all gases contains equal number of molecules. See here, Nana, P1, P2, V1, V2. For example, see here I am taking one block or one container. This is the container number one, and this is a container number 2. Here with pressure P1, with volume V1 at temperature P1. Here at pressure P2. Second one is P2 at volume V2 and at temperature T2. Now from both I am mixing, and here I will get as different pressures, different volumes, different temperatures. But for example, okay, how many number of moles are there? Let us take this. Here it is 2. Okay, here, okay, y2, we will take it as n1. Number of moles is n1, number of moles is n2. Okay, now here in this together, if I consider number of moles will be same, where n1 is equal to n2. This is the Avogadro's law. Okay, next, Dalton's partial pressure mixture law. See here, Nana, this is one container. Okay, in container we have so many identical gas particles, which are spherical, which are tiny, which are small compared to the distance between them, correct? Now all these small particles will exert pressure on the each particle, correct? Now they are moving in all possible directions with all possible velocities. They collide with the each other, right? These particles are now colliding with the each other, correct? So in all possible directions with all possible velocities, they are exerting force on each other. So by with respect to that, we get pressure. What is the pressure? It's a force by area, correct? Now each particle will exert pressure P1, P2. This particle will be P3, fourth particle is P4, Fifth particle is P5. Wait. So here I will redraw this for your better clarification. Okay. So these are the small identical particles. Correct. Each of the particles are colliding with each other. What type of collision? With a perfectly elastic collision. Correct. After colliding means they are exerting a pressure. Now this particle will exert P1 pressure, P2, correct, P3, fourth particle will be P4, fifth particle will be P5, sixth particle will be P6, seventh particle will be 7, correct. Number of moles is equal to number of that many pressure particles. For example, 10 moles, 10 molecules are there. So pressure will be total 10. So pressure exerted by all 10 will be P1 plus P2 plus P3 and so on till P10. Okay. So now total pressure exerted by all the gas will be P1 plus P2 plus P3 and so on till number of particles. So from here I can write it as what is the P1? N1. So first particle is exerting N1 plus N2 plus N3 and so on plus number of N particles. What is the pressure formula, Nana? Pressure formula is equal to mu RT. Correct. PV is equal to mu RT. P is equal to RT by V into mu. Correct. So from here I can take RT by V as common. This will be the answer. Okay. Now P is equal to all number of particles will exert at constant temperature and volume. Now this becomes N1 RT by V plus N2 RT by V plus N3 RT by V and so on Nn RT by V. Okay. So here I can write P1 as N1 RT by V. This is the pressure exerted by the first particle. What is the pressure exerted by the first particle? N1 RT by V. Second particle, how much pressure it is exerted? N2 RT by V. Third particle, N3 RT by V. In this way. Okay. So here total pressure exerted by the gas will be pressure of all individual particles. Okay, so this is called Dalton's law of partial pressure. Okay, ma? Understood? Next, in a closed cylinder, there are 60 grams of neon and 64 grams of oxygen. If the pressure of mixture of gases in cylinder is 30 bar, then partial pressure of O2 in the cylinder is. So it is a closed cylinder. It is a closed cylinder. Here we are having 60 grams of neon and 64 grams of oxygen. So this is a closed cylinder. Okay. If the pressure of the mixture of the cylinder, what is the total pressure they have given? P total is 30 bar. Okay. Partial pressure of O2 in the cylinder is. So you have to calculate what is the pressure exerted by the CO2. When these kind of questions is given, pressure of one particle, okay, is equal to P total, P total into mole fraction will give you the answer. Okay. So here we have to calculate O2 and PT into we have to consider, we have to calculate the mole fraction. Okay. So mole fraction, how will you calculate? Number of molecules in oxygen, number of moles in neon. Number of moles, how many masses, how given mass is how much, what I told, number of moles is equal to number of moles is equal to given mass by molar mass. Correct. So, number of oxygen, moles in oxygen. What is the given mass of oxygen? 64 divided by, no need to change into kgs because anyways the pressure is in bars only. No? So CGS units only we are having, no need to convert. 64, what is the molar mass of oxygen? 16 into 2 it will be 32. Neon, how much mass is given? 60 grams by molar. What is the atomic number of neon? It's 10 into, it will be approximately 20. So this will be how much? 1 zer, 2 zer. Correct. So you will get 2. 1 zer, 3 zer. This I will get it as a 3. Okay. So how many moles is there? 2 moles of oxygen is there. 3 moles of neon is there. Okay. So number of total will be how much? 2 plus 3. 2 plus 3 is how much? 5. 2 plus 3 is how much, Nana? 5. Mole fraction. Now I have to calculate the mole fraction. So, mole fraction is equal to, how to calculate means, number of the particles that we want to calculate. Okay. Number of particles of a given gas divided by total. So, given means for what we have to calculate, Nana? For oxygen. Oxygen, how many are there? 2 divided by total, how many? 5. 2 by 5 is how much? 2 ones are to 2.5. 1 by 2.5 means it is 0 0.4. Mole fraction is 0 0.4. Okay. Now if I want to calculate pressure at 2 will be mole fraction into total pressure. Mole fraction is how much we got? 2.5. This is 0 0.4. Total pressure is how much? 30 or 2.5 only we can write. This will be 30. How many times? 5 ones are 5 6 are. 2 6 are how much? 12 bar. So pressure of oxygen is 12 bar. Correct. Now total pressure is equal to pressure of oxygen plus pressure exerted by neon. Total pressure is 30 bar is equal to pressure by oxygen. How much we got, Nana? Bar is equal to pressure due to oxygen is 12 bar plus, they did not ask to calculate the neon, but what if in case they ask, we have to find out, no, we have to be ready for everything. So pressure for, I think, helium. Okay, pressure for neon will be 30 minus 12. This is equal to how much? 28 atmosphere. Sorry, 18 atmosphere. Okay, 18 plus 12 will get total pressure. Understood, Nana? How to solve this? Please look at this question once. So, in a closed cylinder, there are two gases given. If the pressure of mixture of gases in a cylinder is 30 bar, okay, so how much is given? 30 bar, then partial pressure of O2 in this will be. So, we have considered a closed cylinder, okay, two gases are there, okay, and then we have calculated first. This formula is very important, okay, Nana? Next. Concept of mixture. In a closed system, apply conservation of moles. Okay, concept of mixtures. For example, N1 moles of mass M1 is mixed with N2 moles of mass N2. Okay, find mixture. Okay, so mixture mass will be N1, N1 plus N2, N2 divided by total number N1 plus hydrogen and helium or gases. Hydrogen, helium, gases of volume V at same temperature T and same pressure P are mixed to have same volume. The resulting pressure of the mixing is okay at same temperature and same pressure needs to have same volume also. Okay, so you have to find out the result of mixing pressure. Okay, so N of hydrogen and N of helium. What is the formula? PV by RT. PV is equal to nRT. From here I can write it as RT. Number of NH2O plus NHE will be PV by RT plus PV by RT. Why I am taking PV by RT? Why I am not taking P1 V1 means in the question they clearly, okay, in question they have mentioned clearly at same temperature T, at same pressure P, okay, gases of volume V, which means same volume also. Here also they given or next to have same volume. Resulting pressure you have to calculate. So I can take pressure of hydrogen is equal to pressure of helium, volume of hydrogen is equal to volume of helium, correct? So I can write PV by RT plus PV by RT. So how much together I will get? 2 PV by RT. Now new pressure or mixture pressure, mixture pressure into volume. Anyways, same volume, no? Here, how much we will get? 2 PV by RT. This is N RT into RT. Correct? RT cancel. Same volume cancel. So, mixture of the pressure is equal to 2 times of the pressure. This is the answer. So, answer is third option. Please look at the solution mark. Next, speeds. So, in ideal gas, we have discussed, right? There are speeds, or else they are having random motion by elastic collision. So, gas particles will move in all random directions, in all possible directions, with all possible velocities, right? So, magnitude of velocity is a speed. So, various speeds of gas molecules. We have average speed, root mean, square speed, and the most probable speed. Different speeds of gas molecules. First, we will see what is average speeds of molecules. Okay, for example, if N1 is having V1 speed, like that N2 is having V2 speed and so on. N number of particle is having velocity. So average speed means what? V1 plus V2 plus V3 plus V4, V5 and so on till Vn divided by total number. Average means sum of by total number of particles, right? So from you can write it here. Number, total number will be N1 plus N2 plus N3 and so on plus Nn. This is called the average speed. Okay. Mm. Root mean square speed. This is called VRMS speed, which means that root first. Mean, what is mean? V1 plus V2 plus V3 and so on plus Vn by n. And what is else asked? Square. Correct. So V1 square bar or else V2 square bar, V3 square and so on Vn square. So this is called root mean square speed. The square speed means square. This is VRMS speed. We have one more formula. VRMS is equal to root over VRT by N. This is most probable speed. The particles of a gas have a range of speeds. This is defined as the speeds which is possessed by maximum fraction of total number of molecules of gas. Okay, maximum fraction of total number of will be there. For example, if speeds of 10 molecules are given as 1, comma 2, comma 2, comma 3, comma 3, comma 4, comma 5, comma 6, comma 6. Correct. Most probable speed is 3. Maximum fraction. 1 is, see here, in the given data, 1 is coming only one time. 2 is coming only 2 times. 3 is coming 3 times. 1, 2, 3. And 4, 5, 6 is also coming 2 times. What is the most fraction out of 10? We are having 3 threes. So this is maximum fraction. Correct. So 3 will be the most probable speed. In that way we have to calculate. So most probable speed as maximum fraction of total molecules possess this speed, which means out of 10, how many particles possess? 3 particles. Okay, so that is the most probable speed. Most probable speed is 3RT by m. And also in terms of Boltzmann constant, it is root over 2k by small m. VRMS also we can write. VRMS is equal to root over 3p by density is equal to 3RT by m. This will be equal to root over 2, sorry, 3 kT by small m means mole given mass, capital M means molecular mass. This comparison. Okay. Huh. So at any temperature, velocity of RMS is greater than, this is important. Always very, very important. At any temperature, VRMS is greater than V mean means average speed, NP means most probable speed, and it is also greater than velocity of sound. At any temperature, VRMS is not equal to V mean, not equal to NP, not equal to sound. They will be always greater, they will be not equal. So this is the relation between VRMS. So VRMS one is directly proportional to root temperature. VRMS is inversely proportional to 1 by root over molecular weight. Correct. What is the VRMS formula? VRMS is equal to root over 3 RT by M. So directly proportional to temperature, inversely proportional to the molecular weight. At what temperature root mean square velocity of hydrogen becomes double at its STP and pressure remains constant. V1 by V2 directly proportional to T1 by T2. Temperature only we are here asking. Okay. So if V1 is V, then V2 will be how much? Double times of V, correct? So okay, T2 by T1 we will take. Anyways, we have to calculate the temperature only, right? So we know that Vrms is equal to root over 3RT by molecular weight. Vrms is directly proportional to the temperature. V1 by V2 is equal to root over T1 by T2. This we can write it as V2 by V1 is equal to root over T2 divided by T1. Okay. Now, if velocity of first body is V, then first gas is V, then how much it is increased? It increased to double. So, 2V by V is equal to root over at STP. At STP, what is the constant temperature? It is 20 degrees Celsius. 20 only we can consider. 20 means how many? Hmm, by T2 you have to calculate. This you can take approximately EV gets cancelled by 20 degrees. You can take 20 only, you take square on both sides. You will get how much you will get? Okay, 4 is equal to T2 by 20. T2 is equal to 20 into 40. This becomes, convert it to Kelvin and Kelvin. Okay. Average number of molecules in each direction of wall is given by n by 3, n by 6, sorry. Number of molecules along each axis. See, no? How many directions are there? The number of molecules along each axis will be n by 3, where nx is equal to n by is equal to nz. Okay, if the pressure, this we have written, okay, the pressure, temperature, both are given, then consider only temperature effect. So we have considered only temperature effect will be there. So square on both sides, root 3, root 3, root 3 gets cancelled. So this will be the answer. This will be pressure by density, which is equal to P by D. Remaining constants you know, where K is the Boltzmann constant. Next, RMS velocity of gas molecules of a given amount of gas of 27 degrees Celsius. So T1 is given 27 degrees Celsius plus 273. If you add, it becomes 300 Kelvin. Next, pressure at this temperature, how much is the pressure? 1.0 into 10 to the power 5 Newton per meter. Yes. Hmm. Is VRMS 1 will be how much? 200 meter per second. And here now temperature is increased. So T2 is equal to how much? 127 plus 273, 10, 0, 400 Kelvin. Pressure number V2, VRMS. Sorry. We have to find out at this temperature what is VRMS2. What is pressure P2 given? 0.5 into 10 to the power 5 Newton. We have to find out the RMS velocity. Vrms in terms of temperature will be root over 3RT by M. Okay. So Vrms is equal to root over. So you can take a proportionality constant root T. So V1 by V2 is equal to T1 by T2. What is V1? 200 by V2 you have to find it. T1 is 300 by 400. Okay. So zeros and zeros gets cancelled. So 200 by V2 is equal to 3 by 4. V2 is equal to 200 by 3 by 4. It goes at 4 to 800 by 3. Root is there. Wait, it is having root, root, root. Okay. This is the answer. Hmm? Take 2 out. 2 into 2. 400 into root 2 by 3. So 4 root is there, no? Root 4 value is how much? 2. 2 2s are 400. 400 by root 3. This is the answer. Okay, please go through once. So second VRMS2 is 400 by root 3. Expression for a pressure of an ideal gas. Pressure is equal to 1 by 3 N M by V into V bar. I can write this as 1 by 3 N into density T. This is the pressure. Degrees of freedom. See now. I will take one more slide to explain it again mostly. See, one container I have taken. All are identical particles are there. Okay. Now, each, for example, you consider this particle. You consider this particle. Okay. This particle will move, or else this particle will have all possible velocities. It moves with all possible velocities, all possible directions. Correct. Now, this has a freedom of moving in different directions. How many possible directions are there? 3 directions are there. So, how many possible directions are there? 3 directions are there. Correct. So, it has a freedom of moving in all 3 directions. Correct. So, that movement of the possible particle. Okay. Now, listen here. This will move with possible velocity all possible directions. Correct. So the freedom of movement of each particle is known as degree of freedom. That's it. So number of independent ways. The number of independent ways in which a molecule or atom can exhibit a motion or have the energy, which exhibits energy in all the possible directions. That is the degree of freedom. See, degree of freedom are three types. Transitional means this is only for monoatomic. Transitional is from only monoatomic. Single monoatomic means what? Single atom. So single atom can move in only in three directions: x axis, y axis, and z axis. It has only possibility of having three independent directions. So it can move independently in all three directions. So for monoatomic, what is the degree of freedom? 3. Okay. Rotational motion. In rotational motion, if you see, three are there, one clockwise and anti-clockwise. How many? So in rotational motion, three translational, sorry, in rotational motion, transitional kinetic energy will be in all three directions, it will be correct. So this will be degree of freedom. 3 transitional plus 2 rotational. Here at high temperatures vibrations will be 2 vibrations will be there. 3 transitional means x, y, z. So this is 3 transitional. Like this one rotational, like this another rotational. Okay. Vibration is in 3D motion the body will move. Degrees of freedom table. Monoatomic means single atomic. Monoatomic means it is single atom. Okay, monoatomic means it is a single atom. It will have, monoatomic particle exerts transitional kinetic energy. Only it exerts transitional kinetic energy. So it is 3T. Okay, so it has a 3 transitional kinetic energy. So monoatomic. So you can take a table types. Wait, I will draw the table nicely. Okay, next. Types of gases. Degrees of freedom. Hmm? Next. Oh, first one will be types of gases. Types of gases means how many types of gases we have. Monoatomic, diatomic, polyatomic. Monoatomic means one atom, diatomic means two atom. More than two, you can consider it as a poly. The degree of freedom means in how many directions it has the freedom to move. One particle means it is having 3 degrees of freedom. Diatomic means 3 transitional plus 2 rotational. This is having 5. Okay. Now here polyatomic means it will have at high temperatures detail, right? This you can take it as 3 transitional. Here it will be 3 transitional, here it is 2 rotational. Okay, in poly it will have a 3 transitional plus 2 rotational, and in many cases it will be at high temperatures it will be 2 vibrational also. Then together it becomes a 7 or 6 depending upon the temperature of the gas. 7 or 6. So this vibrational can be 2 or 1. Vibrational, listen here. Vibrational degree of freedom is possible only at high temperatures. Okay, Rana? Degree of freedom for different gases is according to atomicity of gas at low temperature and high temperature. Diatomic molecules will have 7 degrees. So as I told you, at high temperatures it will have 7 degrees of freedom, 3 translational, 2 rotational and 2 vibrational. Okay, next atomicity. Okay, hmm. Maxwell's law of equipartition energy, the total kinetic energy of the molecules is distributed in all degrees of freedom is associated with the. Now the kinetic energy will be half in the Boltzmann constant into the temperature. Internal energy will be degrees of freedom. Internal energy, because you can call it as potential energy or the internal energy. In gas, we are having only internal degrees of freedom by doing K2. You see here, Nana, translational kinetic energy. As I told you, how many will be there? 1 by 3. Okay, so half m v square, half m Vrms square. Vrms, what is the value of Vrms? Will be root over 3RT by m. Square means you can take it as 3RT by m. So half m v square is how much? 3RT by m. Half of terms cancel. 3 by 2 into RT. We know that PV is equal to mu RT. Monoatom means transitional means N value will be 1. PV is equal to RT. From here I can take this as 3 by 2 into PV. This is the derivation for PV. Okay. Or you can also call it as for N number of moles it is 3 by 2 RT also. And this way you get the pressure also. Right. Molar means RT. Molecular kinetic energy means half mv square. This is the answer. 3 by 2 kT. Please note down, Nana. Or else you can take the screenshot also. This is very important. Okay. Next, total kinetic energy U for degrees of freedom. This is for internal energy. This is for internal energy. Next, this is for degrees of freedom. Degrees of freedom means, as I told you, U will be F by 2 RT and U moles it is F by 2, molecules it is KT. Okay, molar kinetic energy or molar mean kinetic energy for 1 mole and per mole. This is for calculation. N1, F1, T1. This is important. Okay, ma? Any doubts? Uh, The temperature of a gas is minus 73 degrees Celsius. To what temperature it should be heated? So average kinetic energy is doubled. We know that Ke is equal to 3 by 2 Kt. Here comparison is happening where K, none of this K is Boltzmann constant. Okay. So if you take it both are constant, I can write Ke is directly proportional to the temperature, where Ke1 by T is equal to the constant. Okay. Now comparison of two gases means this becomes Ke1 by T1 is equal to Ke2 by T2. What happened to this pen? E1. Now Ke2 by T2. What you have to calculate now? The average kinetic at what temperature? Okay. So if it is Ke and here I am taking it as temperature of minus 78 degrees Celsius. Okay. So minus 78 plus 273. How much? 273 minus 78. 13. 8. 13 minus 8 is how much? 13 minus 3 is 10 minus 5. 0, 2. Is equal to 2 times of Ke, and you have to calculate at water temperature. Ke gets cancelled. T2 is equal to how much you are getting? 1 divided by 205 is equal to 2 by T2. T2 is equal to this you go that is this side. This becomes 2 divided by 205. 1s are 1s are 2, 0, 2 2s are 4. Something it will come under minus 73 degrees Celsius means 1 divided by 1.102.25. Somewhere it will get like that. Okay. So 1 divided by 102 means how much it will get? You take the 0, 0, 1, 6. Approximately it is to 0.6, like that it will come. Okay. Next, pressure and energy density relation. We know that energy density means anything by volume. Okay, mass density, mass by volume, energy density, energy by volume, charge density, charge by volume, like that. Okay, energy density means energy by volume. Energy will be 3 by 2 PV and volume, and here you can write total pressure is equal to 2 by 3 times of the energy. Molar specific heat of gas and Mayo's law. Molar specific heat means specific heat of gas. We know that specific heat. What is specific heat? The amount of heat required by mass of substance to increase its temperature by 1 degree Celsius. For example, a body is there, it has been at certain temperature. Now I want to increase 1 degree Celsius more. For example, T is there, I want to increase it by T plus 1. To increase that 1%, we have to give heat, right? So how much heat is required by that substance so that its 1 degree can be raised from the initial temperature, that is T plus 1. Okay. So specific heat of gas means the amount of heat required by 1 mole of gas to raise its temperature by 1 degree Celsius. The required heat is directly proportional to the delta theta. Okay, so Q is equal to temperature, no, see number of moles, and the proportionality constant will be smaller. This M is the molar specific heat. capacity or molar specific heat for the gas. See, isochoric process for different process. Isochoric means volume constant. This I will discuss in the thermodynamics. Okay. Now isochoric means volume constant. Here if I take CQ is equal to mu here at constant volume. C means at constant volume delta T. Here I told no, if you increase the heat given, temperature will be increased, right? The amount of Q is obviously directly proportional to temperature. If heat given to the system is increased, then the temperature in the system also gets increased, right? Correct. So it is directly proportional. How much number of particles will have, number of temperatures, and the constant is specific heat. From here you can write Cv is equal to Q by T. At thermal process means temperature is constant. Isobaric means pressure is constant. Isochoric means charge is constant. This is important. Adiabatic means there will be no, flow of heat. It will not allow. Adiabatic means it resists the flow of heat. Molar specific heat for cap mixture of gases. Suppose we have two ideal gases of this I told mu1 with a heat. Now they are mixed until their temperature changes by delta T. Okay. So mu1 C1 plus mu2 C2 by mu1 plus mu2 will be the mixture. Specific heat mixture will be mu1 C1 plus mu2 C2 divided by mu1 plus mu2. This is the formula. 3 moles of monoatomic gas is heated at a constant pressure from 27 degrees Celsius to 227 degrees Celsius. The amount of heat required in terms of R. 3 moles of monoatomic gas. Amount of heat required. So Q is equal to, okay. So what is the formula? Change in temperature. Directly, it is directly proportional to change in temperature. Directly proportional to what is the change in temperature? 227 minus 27. Q is directly proportional to how much? 200 degree Celsius. Now convert it into Kelvin. So temperature is directly proportional to 473 Kelvin. Okay, 3 moles of monoatomic gas is heated. Okay, so we have to find out amount of heat required. So Q is equal to N CV delta T. Q is equal to, what is N? 3 moles of gas. 3 monoatomic at constant pressure. At constant pressure means you have to take it as Cp here. Cp and delta T. Delta T is how much? 473. See now, for Cv it is F by 2R. For Cp this is F by F. F by 2 R plus R. This will become F by 2 plus 1 into R. This is for molar specific heat volume and molar specific heat pressure. Now this Q is equal to 3 into 5R by 2. For monoatomic degrees of freedom is 3, right? So 3 by 2 plus 1, how much? 5 by 2 into R, it is R. In terms of R only they asked, right? Correct. Okay, we can consider this is in all. Okay, we will consider this as degree Celsius only we will take. Okay, change in temperature will be how much? 400. This is also we can consider as 400. 2 ones are 200s. 3 5s are how much? 15, which is equal to 1500 R. This is the answer. 4 moles of monoatomic gas and 2 moles of diatomic gas. Find the value of adiabatic constant of the mixture. See, Nana, here I want to tell you molar specific heat at a constant volume. At constant volume, molar specific heat, molar specific heat at a constant volume, it is CV. At a constant pressure, it is CP. Now we have one Maer's relation or law. Molar specific heat at constant pressure minus molar specific heat at constant volume is equal to R. R is a universal gas constant. Here C will be by 2. Cp will be F by 2 R. R plus R. This you can write it as F by 2 plus 1 into R. Here adiabatic constant, one ratio is there. Adiabatic, which is of symbol of gamma. This is ratio of pressure to ratio of volume. So gamma is equal to Cp by Cv. Now from here I can write Cv is equal to gamma by 1 minus R. Cp is equal to gamma into R by 1 minus R. This is for Cp in terms of, and this is Cv. So this is the formula. Okay, understood now? Now, if I take mixture of gases, N1 with N1 mixed with N2, N1 moles of N1 is mixed with N2 moles of N2. Find mixture of following. You have to find the mixture of the following. First one, total weight is equal to mu1 n1 plus mu2 n2 divided by mu1 plus mu2. Okay, second one, CV mix n1 CV1 n1 CV1 plus n2 CV2 divided by n1 plus n2. Next, third one, CP mix n1. This mu1 and n1 are both are same only, now, which is represents the number of moles. N1 n2 n1 plus n2 n1 cp1 plus n2 cp2 divided by n1 plus n2. Next, adiabatic mixture will be cp mix minus cp mix, or else you can also write f mix by 2 plus 1 gamma mix is equal to. Okay, next, F mix means number of moles with the degrees of freedom and N2 of moles with the degrees of freedom is mixed. Then this will be F mix. So depending upon the what is given in the question, you can take it. Okay. 4 moles of mono. We have to find out gamma for the mixture. Okay, first we will calculate gamma mix only. Okay, 4 moles of monoatomic gas and 2 moles of diatomic gas is given. Okay, you have to find the gamma for the mixture. You try this question. Okay, try this question. Okay, next. Next one is mean free path and real gases. Mean free path means mean free path and real gases. A molecule in its path undergoes a number of collisions, so the path gets transferred, right? So it undergoes a number of collisions, so its path gets transferred, correct? So its path gets transferred by not only a single strain but somewhat zigzag. Between two successive collisions, a molecule travels in a straight line, okay, with uniform velocity. As the motion of random does, the distance traveled by molecule between two successive collisions is not always equal. So the average distance, this is the important. Listen, the average distance traveled by the molecule between two successive collisions is mean free path. Okay, so mean free path is denoted by lambda. Mean free path is denoted by lambda. So this is the formula. Lambda is equal to 1 by root 2 pi d square into n, where d is the diameter of the molecule, small n is the number of molecules per unit volume. Next, at what temperature will the RMS speed of oxygen molecules will just become become just what is it, sufficient from escaping from the Earth's atmosphere? Escape velocity is 1.1 into 10 to the power 4 meter per second. Escape velocity from the Earth. Okay, so here they are asking us to equate Vrms is equal to Ve. That's it. Okay, so V square is equal to 3RT by N. Okay, in Boltzmann constant they given a no. In Boltzmann constant, if you can take it as 3K 3 by 2. So how much? What is the formula? Hmm. See, in Boltzmann constant. What is the formula in Boltzmann constant? 3 by 2 K T. Correct. So it is 3 by 2 KT. Okay. So you can calculate temperature from here. V is equal to T root T. Okay. At what temperature means just become sufficient from Earth's velocity. At what temperature you have to just find out. That's it. Okay. So take E is equal to V, substitute the values and we can find out. Next, air bubble of volume 1 meter cube rises from the bottom of the lake and 40 meters deep at a pressure of 12 degrees Celsius. To what volume does it grow when it reaches the surface which is at a temperature? So here you have to calculate the temperature. Okay. So first pressure, how much air bubble of volume V is equal to 1 centimeter cube. This becomes 1 into 10 to the power minus 6 meter cube. No, sorry. 9, 10 to the power minus 2 into 3 to 6 only. Temperature, how much it is given? T is given as 12 degree Celsius, convert it into plus 273. How much? T is equal to 582 Kelvin. At what volume does it grow when it reaches the surface at the temperature? So P1 V1 is equal to T1, P2 V2 is equal to, you can consider it as P2. So P1 V1 by T1 is equal to P2 V2 by T2. Pressure will be atmospheric pressure. So P1 will be atmospheric pressure 1.103 into 10 to the power 5 P naught, plus density is given mass by volume, you consider. What is mass given? Deep at 35 degrees. Okay, so from here rho g h. So 1.103 into 10 to the power 5 into 10, sorry, plus what is the height? 40 meters, and acceleration due to gravity plus 40 into 10 plus density. It reaches the surface at your top. Okay, volume 1, what is mm, mm, temperature. So anyways, density gets cancelled, no problem. So P1 you can consider how much? Approximately 40 400 plus 1. Some it will come around some 40.03 into 10 to the power 5, something like this. Okay, now you consider P1 is how much? 41.03 into 10 to the power some 6 by into volume is how much? 1 meter centimeter cube, which is 10 to the power minus 6. T1 is a temperature 12 degrees Kelvin slope. If you convert it will become 285. P2 is 1 atmospheric pressure 1.105 into V2 you have to find out, divided by temperature 35 degrees. 35 means it will become 295. So from here V2 is equal to 41.03 into 10 to the power 8 into 1 into 10 to the power minus 6 into 295 divided by 285 into 1.05. So 295 into 45. So from here approximately this becomes 1 into 40 by 8. So this becomes 5. Somewhere velocity V2 will be, you will get it as 5.263 into 10 to the power minus 6 meter cube. So this is the answer. Next, read the question. Read the question mark. Pressure exerted on the walls of the container by a gas is due to the fact that gas molecules are changing their momentum due to collision with the walls. Statement 2. The molecules of gas collide with each other and the velocities of molecules change due to the collision. Both statement 1 and statement 2 are correct. That's it, Nana. So we have revised every topic in detail from kinetic theory of gases. Now we are going to start thermodynamics. Okay. So now we are going to start thermodynamics. I hope you all understood the kinetic theory of gases. One question I gave it as a try. You can try that question and comment the answer below. Okay. So next, thermodynamics, law of thermodynamics, internal energy and work done, thermodynamic processes, heat engine, heat pump, refrigerator. One more thing is there, that is Carnot engine. That is Carnot engine we are going to discuss now. This is the previous paper analysis. If you see, each and every year we got at least minimum 2 questions. So this is very important. So 2 to 3 questions is the weightage of this chapter. 2015 it is 2, again 1, 16 again it is 2, 1, and again in 17 it gave one question, three questions in 18, three questions in 2019, one in 2020. Okay, again two questions in the examination 2021. In 2021 it is not given. 2022 one question, 2023 one question, 2024 also one question. So consistently we are getting one or two questions. Thermodynamics. So what is this thermodynamics? It is a study of flow of heat. Is thermodynamics. The study of flow of heat is thermodynamics. So thermodynamic variables, these are two ways we can classify: state variables or functions, or path functions. These two does not depend on path. Okay. State variables does not depend on path, they only depend on state. Example, internal energy, pressure. For example, we are taking like this. Okay. From here to here, if it is taking U1 energy from A to B, okay, from here to here, it is taking the same U2 energy. Here U1 is equal to U2 because both the particles initial state and the final state both are same. This is initial state, final state same, and this is also initial state and final state are same. So path is not dependent. Okay, only state is dependent. Path functions only depend on path, which is work heat. Okay, so change in the size of a system depend on the quantity. It independent of quantity or size is pressure, temperature, density. These are, you have to know all these things. Okay. Zeroth law of thermodynamics. What is the zeroth law of thermodynamics? Is, for example, okay, this is A body, this is B body is there. For example, temperature A is greater than temperature B. What happens when two unequal temperature bodies are kept in a contact? Heat from higher body temperature transfers to lower body temperature. Correct. Now here what will happen? Temperature from higher body gets transferred to temperature of lower body. Until what time it will be, transferring? Until both the bodies get the equal temperature, so heat transfer will be there. Correct. So until it will become Ta is equal to Tb. Now this is called thermal equilibrium. What is thermal equilibrium? When the two bodies has to attain same temperature through the transfer of heat. When a high temperature body is kept in contact with a low temperature body, the heat transfers from high body temperature to low body temperature. Correct. Now this transformation will happen till both the bodies get same temperature. So T1 will be equal to T2. This is the point. Now here Ta temperature of the body and the temperature of A body and B body both are equal. So Ta is equal to Tb now, which means that both A and B are in thermal equilibrium, means at a heat equilibrium. There is nothing to transfer even if they are keeping in contact, because both are having same temperature. Now when two bodies are already in the temperature, I mean thermal equilibrium, now I am adding one more body, that is C. Okay. And here what I am doing is, between A and B, whatever the heat transfer wall is there, I am closing it. Means through A to B, now heat is not transferred. Now what happens? A goes to C, C goes to, from A heat goes to C, from C heat goes to B. Again three bodies are in thermal equilibrium. This is what zeroth law of thermodynamics is. When two bodies are kept in a contact with each other, when two thermal bodies, thermal equilibrium bodies are kept in a contact with another body, that body also will become in the thermal equilibrium state after some time. This is what zeroth law. Now internal energy. Internal energy is directly proportional to the temperature. U is equal to this mole into some constant. into delta T. U is equal to N. If at constant volume means CV delta T, at constant pressure means N Cp delta T. At constant volume, at constant pressure. This you in terms of degrees of freedom, U by 2, U is equal to F by 2 RT. That's it. Okay. Next, work done. Here, what is the work done? Listen, no? Whatever mechanical work we are done, it produces a heat. Best example I am doing, for example, my hands are like this. I am rubbing towards each other. Now I am doing the mechanical work, correct? I am applying force and displacement is happening, and this is rubbing of hands against each other. I am doing the mechanical work. So after rubbing, what I will get, there is a heat produced. So the amount of work I am doing, the amount of heat it is being produced. Okay. So here work done is directly proportional to the Q net. Okay. Now we know that work done is equal to force into displacement. Work done is equal to force, small work if we take, it will become dx. Total work done will be dw, that is equal to force into dx. Okay. Next, we know that pressure is equal to force by area. Force is equal to pressure into area. Substitute it here. Integration of dw is equal to integration of pressure into area into dx. Can I write change in volume, small volume or change in volume is equal to area into dx. This is thickness. So volume is equal to area into thickness. I can take this. Okay. So work done is equal to integration of pressure into volume from V1 to V2. This is the equation. Okay. From here again we are having so many formulas. So work done is equal to pressure into V2 minus V1 at constant pressure. Okay. Work done is equal to P2 minus P1 into V2 minus V1 at variable pressure. Okay. Next, if change in volume is 0, then it is work done also 0. These are the formulas. Next, this is first application, this is second application, this is third application, this is fourth application, fifth application. Area under pressure and volume gives work. This is fifth application. Example, pressure, volume is there. This is the graph. Here you can take this as V2, here you can take this as V1, this as P1, this as P2. What is the area work done is equal to area under PV graph. What is the area of a triangle? Half into base is how much? V2 minus V1. What is height? It is P2 minus P1. This is the work done. Next. Some like this it is there. Volume, pressure. This is V2. This is V1. P1. P2. What is the area work done is equal to area will be pi R1 R2. How it is means So from here to here, if I take by 2, this will be R1. If I take it here by 2, this will be R2. This will be R1. This will be R2. So you can take it as work done is equal to pi B2 minus B1 by 2 into P2 minus P1 by 2. This you can take it. Okay. Or else this you can also take it as work done is equal to pi into P2 B2 minus P1 P1. In this way also you can take. First law of thermodynamics. What is this first law of thermodynamics? For example, if this is the system, these are the particles. Okay, you are giving heat. Heat, no, we will draw yellow color, orangish. Okay, we will take some yellow also. Now I am giving heat. Okay, now total amount of heat I am giving Q means heat given to the system. Okay, whatever heat I am giving to the system, it will be divided into internal energy plus work done. How it will be there means, listen here, this I am closing with a small piston. Take one small piston like this. It will be like this, closed, and there will be one handle for it. Okay. Now what happens? I provided heat to the system. By observing the heat, it will move. The gas particles will get expand. Best example means boiling of water, boiling of rice, boiling of milk. You keep milk on the stove, and then you know after few times or after few minutes of time or few moments of time, milk will started come out of the boil. That means it is expanding. Correct. So if we keep plate, for example, milk is there in a container or a vessel. I have placed one lid on it, placed it on a stove. Now I on stove, milk is coming, means expanding. Okay. Instead of milk, you can assume it is a gas. So it is expanding, and along with the milk, the plate gets up, correct? In the same way, here gas is there. I am providing heat, and then gas is this is moving the piston upwards. Okay, or else now we are making this whatever the piston it is moving, let us take that the distance as dx. Okay, so I mean increasing the volume or decreasing the volume to happen, so it will come. So internal energy, internally the heat is observing by the particles, correct? Heat observed by the particles, and few whatever heat you are giving, internally they are observing some energy, and externally they are doing some work. So this is Q is equal to delta Q plus double V. Sign conventions. Heat absorbed by system. In case if system is absorbed, then it is a positive charge, positive heat, sorry. Heat rejected, removed by system means it is negative. Positive Q, negative Q. Positive U. See, if you are increasing heat, temperature increases. Temperature increasing means particles are absorbing more heat. As they are absorbing more heat, temperature increases. So temperature increases means energy will be positive. Internal energy, I mean to say. Okay. If negative energy, temperature decreases, minus energy. Work done. Positive work done will be work done by gas. I will tell what is by gas. Work done on the gas. Work done by the gas is positive. Work done on the gas, it is negative. See, listen here, Nana. What is work done by the gas and on the gas? By the gas means gas particles will absorb heat and it will expand. By expanding to occupy the area, it will push the piston up. This is work done by gas. Okay. Now to balance it again, I am putting force here. This is work on the gas. Okay. Internal energy of the system. See, Nana, 1 calorie is equal to 4.2 joules. Please remember this. Internal energy of the system changed by observing. Heat is observing here. So positive. Q is equal to delta U plus work done. Q, how much it is there? 2 into 4.2 joules is equal to work done by the gas. Means positive only. On the gas means negative, no? 500 joules. In the system it is observed, you have to find out the energy. So energy is equal to 8.4 minus Q. We have to find the energy only, no? What is the work done? 500 joules. This kilocalories, correct. Kilocalories, no? Kilocalories means it will be 4.2 into 10 to the power 3 joules. 10 to the power 3. 8.4 into 10 to the power 3 minus 500. 8,400 minus 500, 7,900 joules is the answer. Okay, please have a look now. Nice. System is taken to the from the state A to state C by two paths ABC and ADC as shown in the figure. Listen, Nano. DU1 is equal to DQ1 minus DW1. 50 joules minus 20 joules. How much? 30 joules. This is DU1. Heat absorbed by amount of work done we have to find out. Anyways, volume is a constant only, right? So dq2 is equal to 36 joules. dw is equal to dq2 minus energy 36 joules minus 30 joules. This will be 6 joules is the answer. This is a NEET 2013 question. Thermodynamic process. Okay, isochoric, isobaric, adiabatic, isothermal. Okay, listen here now. Isochoric means change in volume 0. P D. This is the isochoric. Next, B T. Next, here work done is 0. Whatever heat you are giving, it is completely change in internal energy only. P T constant. Okay. Isobaric. Change in pressure is 0. There will be no change. Pressure is constant. So here whatever energy you are giving, it is for both energy and work done. Pressure, temperature, pressure constant, pressure, volume, pressure constant, volume, temperature. It will be like this pressure. Next, adiabatic. Next one is isothermal. We will take isothermal. Delta T is equal to 0. PV graph will be straight. B will graph pressure and time graph for temperature graph. Next, adiabatic. PV power gamma is equal to the constant. This is the equation. PV is equal to the constant. Slope of adiabatic process is equal to minus of slope of isothermal. This is the important. This is equal to minus dP by dV. The ratio of specific heats of a gas at constant pressure to that at a constant is gamma in change in internal energy of a given mass of the gas when volume changes from V to 2 V at constant pressure. Okay, so at constant pressure we have to find out what we have to find out the change in internal energy. So change in internal energy at constant pressure will be mc delta T. Okay, so you can take the ratio of constant pressure Cp to Cv. You can try this. It is easy question only. Okay, try this question. Next, 1 molar of an ideal diatomic gas undergoes a transition from A to B. So this I told you, no, you can simply consider work done is equal to, okay, PB BB minus PA VA. This is equals to 5 fours are how much? 20 minus 12. How much? 8 volts. Or else you can also take it this as like triangle, half into base into height you consider. Okay, so half into base is how much? 2 into height. It will be path as from the change in internal energy. Yeah, change in internal energy you have to find out. Okay. So change in internal energy will be how much, Mana? 2 into 10. This is also the graphical question. We can get this as, okay, 1 mole of diatomic means it is 3 by 2 into how much you are getting, 20 minus 12. This is 3 by 2 into 8 to 1 are 2 4 are. Then also it is coming 12 kilojoules. You can change one option. So it is 12. The relation between specific heats, that only Cp by Cv is equal to gamma. This we have discussed, right? Pi into how much we can get, 3V0 minus V0 by 2 into 3P0 minus P0 by 2. This we can get it as 5V0 P0. Pi value is 27 by P0 V0. Polytropic process. This is also PV power gamma. Listen here. PV power T, it will come. PV power T will be equal to the constant. This is a polytropic process. Okay. Next, monoatomic gas. C is equal to K power T. So you have to find out more at mono C is equal to by 1 minus N by gamma. This will be equal to gamma by 1 minus, here N value will be the minus power gamma. Correct. So this will be minus gamma by 3. This is the answer. Monoatomic, right? Reversible and irreversible, this is not there for me. Second law of thermodynamics. Heat engine. This is again important. Source, it is connected to, or else you can also call as hot body. This is working substance. Next, sink. This is at Q2. This is at Q1. This is like cool, matlab low temp, low hot body. So work done here will be there. So whatever work done is there, efficiency will be work done by heat given. So from the heat given, how much it is utilized. Okay. So work done will be Q1 minus Q2 divided by Q1. 1 divided by Q2 minus Q1. Percentage means into 100 you can do it. Okay. This is the heat engine. Next, Carnot engine. Carnot engine we are having isothermal expansion. First is isothermal expansion. Second one, adiabatic expansion. The third one is isothermal compression. Fourth one is adiabatic compression. Okay, this is the second I'll have water. So isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. Okay. So for example, if this is the system we are considering. Initially, it is here at this point isothermal expansion. So this is P1 V1 and here it is P2 to V2. This is isothermal expansion. From here again it is adiabatic. This is P3 V3. This is adiabatic expansion. Okay. From here to here again this is isothermal compression. From here to here again it is adiabatic compression. Okay, now work done in isothermal. Here it will be, this is the diagram. One second now. Work done in isothermal. Expansion. Work done is equal to 2.303 nRT log of V2 by V1. Next, all work done in, this is isothermal expansion. Next, adiabatic expansion. It will be P2 V2 minus P3 V3 divided by gamma minus 1. This is the Archimedes formula. Okay. Next, isothermal expansion. Sorry, isothermal compression. Okay. From isothermal compression, work done is equal to, we can consider it as 2.303 nRT log of V3 by V4. This is isothermal compression formula. Next, adiabatic compression. Adiabatic compression. Work done is equal to P3 V P4 V4 minus P1 V1 divided by gamma minus 1. Okay. So please remember all the formulas now. Okay. Next, the efficiency of a heat engine working in between boiling point and freezing. Boiling point of the water and freezing point of the water. You have to try this question, boiling point and the freezing point. Next, first law of thermodynamics is a restatement of principle of conservation of energy. Work done by a gas is a process. It is independent but only depends on final energy. First statement C. Work done is a path dependent. It depends on path, not even the final state of that. The statement 1 is true and the statement R is false. Okay, Nano. First we will see what we have done till now. Okay. So we have studied about thermodynamics, laws of thermodynamics, internal energy and work done, isothermal, heat engine, refrigerator, and also the Carnot engine. Okay, that is about the thermodynamics and KTG. Solve more and more numericals. Okay, whatever formulas we have discussed today, solve more and more numericals on that. Okay, okay, thank you.